where the brain gets its information and where it delivers various hormonal structures. Where the brain gets its information is via circumventricular organs. Circumventricular organs are think about them as windows into the brain. These are areas where you could either sense some information or you could secrete a substance through. And these will be important throughout the course, and when they come up, we'll also bring them back into play. So we will utilize these in different organ systems. But our sensory circumventricular organs usually involve the subfornical organ and the OVLT. These are going to be important in the renal system for helping us to control body osmolality. We also have areas such as the area of postremia that will be involved with helping us sense our oxygen and carbon dioxide concentration levels in the respiratory component of the courses. The secretory portions of the circumventricular organs, and these involve various secreting substances. So you're going to now release something out of them. This will be important things like the pineal gland. This releases melatonin. Melatonin is a hormone associated with the circadian rhythms, and you'll release it more at certain times of the day versus others. We also have places like the median eminence and the posterior pituitary. We will utilize this in the endocrine section because these are going to be areas in which some of the hormones can leave from. Like from the posterior pituitary, it's where oxytocin, antidiuretic hormone, are released. From the median eminence, we have all of the hypothalamic pituitary axis hormones. Now, where is the fluid that travels around the brain coming from, and how is that regulated? Cerebral spinal fluid comes from coracoid plexes. These are located in the ventricles, primarily the third ventricle of the brain, as well as in the fourth ventricle. These are places in which you're going to be able to secrete fluid into. Then you can see it circulates around in the brain and will eventually return to the lymphatic system. It's important to remember that the brain fluid is integral to make sure that neurons survive and thrive. But you can't have too much of it around, or what will happen? The brain is encased in the skull. Therefore, if you try to expand it, it is going to start damaging those neural tissues. So you have to make sure the pressure stays low in the cerebrospinal fluid. But these coracoid plexes will be making this fluid the whole time. How does it do that? And what are its constituents? Cerebrospinal fluid is made up of a little bit higher sodium than what is located in the plasma. Potassium levels are pretty similar. There is less calcium. Magnesium levels are similar. Higher amounts of chloride, a little bit lower glucose, a lot lower protein. And then pH is also lower. So seeing this, you want to think to yourself, what are some of the differences in cerebrospinal fluid? Higher sodium, lower calcium, higher chloride, lower protein, and lower pH. Those are the 5 big ones. So let's talk through how cerebrospinal fluid through the coracoid plexus is produced so that it has slightly different constituents than what are located in the plasma. That can probably be best seen at this type of diagram. So let me orient you because this is going to be a different picture than what we've seen some before. You want to think of the brain interstitial fluid. That is the fluid from the plasma. You want to think of the CSF, which is the cerebrospinal fluid. That is what's going to bathe all those neurons. Be located in the ventricles and so forth. Different than many of the different endothelial transport mechanisms, the sodium-potassium ATPase is located on the apical membrane rather than the basolateral. Almost all other tissues in the body, it's located on the basolateral end. And that's an important concept to keep in mind. The other important things are what were the ions that we wanted to pay attention to. We wanted to pay attention especially to sodium, chloride, and bicarbonate. So let's look at those three specifically. Hopefully you can appreciate in a diagram like this that bicarb is transported across the apical membrane in high concentrations. It's co-transported with both sodium and chloride. This is telling you that you need bicarb in the cerebral spinal fluid. To be able to get bicarb there, you're going to also transport a little bit more sodium and a little bit more chloride. And that is the reason why those are also elevated in the cerebral spinal fluid. So why do you need the bicarb there? It's because you don't have any proteins. Your protein level in cerebral spinal fluid is really, really low. And without proteins around, you lose some of the buffering capabilities that you have in the blood. Therefore, you need to have a higher amount of bicarb in cerebral spinal fluid. How do you get that extra bicarb? You're going to have to break down combine CO2 and water to carbonic acid, have that dissociate into hydrogen ions and bicarb. So if you are moving the bicarb across the apical membrane, you're going to have to do something with those hydrogen ions. How do you do something with them? You pump them across. So you use this sodium hydrogen ion exchanger to get rid of the hydrogen ions. That creates a little bit lower pH in cerebral spinal fluid than what occurs in the brain interstitial fluid and in the plasma.